In this video, we will teach you hypothesis testing, a useful tool in statistics. In lots of situations, assertions have to be validated as to whether it is true or not. For example, we have an option to choose whether to invest in a project. With the data of the past few years, should you invest in it? Or in other words, is it profitable? What we do in hypothesis testing is that we make a judgment whether the condition is satisfied. Okay, let's look at the stock price of Facebook. Obviously shown, the stock price of Facebook has an increasing trend. We may guess the average of the daily return of this stock is positive. However, if we plot the daily return directly, the daily return fluctuates up and down around zero. And our assertion that the average of daily return is positive is not obvious, we have to prove it more rigorously. It is also not obvious as to whether the average of daily return is zero or not. Let's look at the histogram daily return. It is approximately symmetric above zero. It is still not obvious enough as to whether the average daily return is, or is not zero. We must use a quantitative statistical tool to make a rigorous judgment about the assertion that the average daily return is, or is not zero. In statistics, hypothesis testing uses sample information to test the validity of conjectures about these parameters. Let's start talking about hypothesis testing in a more detailed manner. The first step is to set up a hypothesis. We have a null hypothesis and an alternative hypothesis, denoted by H0 and HA usually. The null hypothesis is an assertion we are against. We want to either reject or not reject it. The alternative hypothesis is a conclusion we accept whenever we reject the null hypothesis. Hence in our example, the null hypothesis is the population mean, mu, the average daily return is 0. And the alternative hypothesis, the average daily return, mu, is not equal to 0. Whether to reject, or not reject, the null hypothesis is a sample-based decision. Intuitively, given that the null is correct, the difference between sample statistic, x bar, and the population parameter, mu, must be small enough. But what is small? How do we define small? If it's not small, or we say significantly large, the null should be incorrect, and we should accept the alternative. To measure the magnitude of the difference, we need to consider the standard deviation of the sample as well. This is because the sample with a large standard deviation usually has a larger magnitude, hence, we need to do standardization. In hypothesis testing, we start with the assumption that the null hypothesis is correct. Hence we know the population mean is 0. But in most situations, population standard deviation is unknown. We then replace the population standard deviation with the sample standard deviation. Then this new term denoted as d hat, has a new distribution, t distribution, which is similar to z distribution. The t distribution is still symmetric at 0 and has bell-shaped. However, t has a flatter tail, due to the degrees of freedom. As the degrees of freedom increase, the t distribution will be more and more similar to that of the z distribution. You can imagine that z distribution is a t distribution with infinite degrees of freedom. We will not go through this topic in a detailed manner. Okay, for the next step, we can compute z hat using Python. We will first talk about how to find z hat. First, we have to find the sample mean and standard deviation using the log returns. Then we can find z hat using the formula. When we print the result, we can see it is about 3.385, which is quite a lot greater than 0. Is this z hat a lot greater than 0? How do we define a lot? To answer this question, we have to set up the decision criteria. We first have to decide on the significance level, alpha. Let's fix it at 5% in our example. We will adopt a two-tailed test in this example. We use what we have covered in the last video to find z left and z right, which are -1.96 and 1.96 respectively. These two are indicated in red are called rejection regions. If statistic z hat falls into the rejection region, we can conclude that the statistic is far away from 0 significantly, and thus we should reject the null. Let's talk about type 1 error. Z hat is still possible to take values in the rejection region even if the null is correct, and the mu equal to 0. This chance is equal to alpha, which is 5%. In other words, we have a 5% chance to reject the null hypothesis wrongly. This is called a type 1 error, and the type 1 error is identical to the significance level. If a significance level, alpha, is small, then, the type 1 error is also smaller. Here, we demonstrate how to get the quantiles, which are also called critical values. Let's look at the codes on the right. Norm.ppf can be applied to get the quantiles. We use it to compute the z left and z right. We then compare these two with z hat to see if z hat falls inside or outside this interval. Then, we can draw a conclusion as to whether to reject the null hypothesis. As we have mentioned before, our conclusion may be wrong, but it happens only with a 5% probability. We may want to further demonstrate that the average return is in fact positive. For this hypothesis, we cannot use a two-tailed test. We need another kind of test, which is the one-tailed test. In the one-tailed test, the null hypothesis, which we are against, is that the average daily return is less than or equal to 0. The alternative hypothesis, the average daily return is positive. The decision criteria of the one-tailed test and two-tailed test are different. The rejection region of a one-tailed test is only on one side. Another way to do the hypothesis testing is called the p-value. We know that the null hypothesis is correct, and the standardized sample mean follows z distribution. What is the probability that, for this distribution we are considering, to take an even more extreme value than our observation in the given sample? This is called the p-value. If p is less than alpha, we conclude that the null hypothesis is unlikely to be true. Let's look at the codes. We will focus on the last 3 lines of codes. Here, we use norm.cdf to compute the cumulative probability. After that, we just have to compare it with alpha, and print out the final result, whether to reject it or not. In this video, we have discussed another quantitative tool, hypothesis testing, which is very useful when we have to validate an assertion about the population. In the next topic, we will use all knowledge we have learned so far to explore the relationship among different variables. This can help us to build a prediction model, typically a linear regression model, in the stock market. See you in the next video.